Welcome to a lesson on the curl of a vector field. The goals are to define a curl of a vector field and then also to determine the curl of a vector field. The curl of a vector field f is equal to the cross product of the differential operator, which you can think of as a partial derivative operator and the vector field f. And we can determine this cross product by evaluating the three determinant where the first row would be I, j, and k. The second row would be from this differential operator where we have the partial derivatives with respect to x, y, and z. And the third row would be from the components of a vector field f. And if we evaluate this 3 by 3 determinant, we end up with a vector field with x, y, and z components, as we see here. And in our example, we'll take a look at how evaluating this determinant gives us this vector field. But let's first talk about what the curl of a vector field means. The curl of a vector field measures the rotation or the spinning effect. If you were in a windstorm, the curl would measure the tendency of something to rotate in windstorm given by a vector field. Let's consider this first example. We're going to determine the curl of a given vector field and then determine the curl vector at the given point. So let's go ahead and set up this 3 by 3 determinant to determine the curl of a vector f. So the first row will be I, j, and k. The second row will be the partial derivative operators with respect to x, y, and z. And the third row will be the components of the vector field f. So I'll have x squared z, negative 2xz, and yz. To evaluate this, we'll use the cofactor expansion method. So for this first 2 by 2 determinant, we eliminate row 1 and column 1. So we'll have our partial derivative operators here and then negative 2xz and yz. Here, we'll eliminate row 1 and column 2. So we'll have a partial derivative operator with respect to x and z. And we'll have x squared z and yz. And for here, we'll eliminate row 1 and column 3. So, to determine the x component of the curl, take the partial derivative of yz with respect to y. That will give us z minus the partial derivative of negative 2xz with respect to z. So, we'll have minus negative 2x. And for the y component, we'll have the partial derivative of yz with respect to x. That's going to be 0 minus the partial derivative of x squared z with respect to z. That would be x squared. And then, for the z component, we'll have the partial derivative of negative 2xz with respect to x. That will be negative 2z minus the partial derivative of x squared z with respect to y, and that would be 0. Let's simplify the equation. So we'll have z plus 2x positive x squared and negative 2z. So notice that the curl of a vector field f is another vector field. Now, we want to determine the curl at the point 6, negative 3, and 1. So, the x component will be z plus 2x. It's going to be 1 plus 2 times 6, that will be 13. The y component is going to be x squared, that will be 6 squared or 36. And the z component is negative 2 times z or negative 2 times 1. We now get the value of each component of a vector field.
For our second example, the theorem we're going to use, it says if f is a vector field defined on all of R3, and the component functions have continuous partial derivatives, and the main result says the curl of f is 0, then f is in fact a conservative vector field. So basically, it says we have to compute the curl of the function. If it's 0, it's conservative. If it's not 0, it's not conservative. Okay, so we're gonna take del and cross it with our vector field. So we got our components I, j, and k. So we're going to take the partial with respect to x, the partial with respect to y, the partial with respect to z, and the components are 2xy, we have x squared plus 2yz, and we have the component y squared. And we're going to calculate using cross product. So it says the partial with respect to y of y squared, that's simply 2y, minus, if we take the partial with respect to z of the x squared, well, that's just 0. Then we've got 2yz, and if we take the partial with respect to z, that's just 2yi. Then, if we take the partial with respect to x of y squared, that's simply going to be 0. If we take the partial with respect to z of 2xy, that's also 0j. And then, if we take the partial with respect to x of x squared plus 2yz, we simply get 2x minus, if we take the partial with respect to y of the 2xy, we simply get 2x. K. Everything cancels out, and that simply leaves us 0i plus 0j plus 0k equals to 0. It says, in fact, that the curl of our vector field turned out to be 0, so it is conservative.